students, I hope you don't crack up during the lessons this week, but we are going to be talking about the crust of the earth in pieces, kind of like a broken eggshell, of a hard-boiled egg, that is. But our topic this week, as you know, is plate tectonics. So let's start talking a little bit about plate tectonics. We don't have too many notes during the course of this week. And as they say, a picture is worth 1,000 words and a video is worth 1,000,000 words. So I'm going to be showing you a number of videos this week to really illustrate some of the things. But with our notes, I do want to summarize some of the more important concepts that we will be focusing on with plate tectonics this week. As I said, I'm going to be showing you some videos. This was a really cool video. I think I showed it to you before this video lesson. If not, I'll show it to you after the video lesson, but really, really cool. Linked as well in Google Classroom. So let's discuss some of our notes from plate tectonics, and in a very simplified fashion, plate tectonics involves the movement of rocky slabs across the earth. And again, the videos show this so much better, but we have what are called convection currents under the crust of the earth, where we've got hot molten material bubbling up, and as a result, there is a movement of material in a layer called the asthenosphere, on top of which the lithosphere, or the hard rocky slabs of the earth, are floating. Yes, we are floating on the surface of the earth. Even though we're not on top of an ocean, we are floating on top of an ocean of molten rock. I mean, that's pretty cool when you think about it. But the surface of the earth, the lithosphere of the earth, is moving from one place to another as a result of that molten material. It's in a similar way, that's how Earth's weather is formed, the movement of air from one place to another. But in terms of plate tectonics, it is the actual rocky slabs called the lithospheric plates that are moving from one place to another. In fact, if you look at these pictures here, think about the Earth as a hard-boiled egg. And I'm sure you've all seen hard-boiled eggs, and you can crack the shell and remove slabs of the shell. When I was younger, we used to have what we called egg dibbies. During Easter time, we would hard-boil eggs, and we would color them and hide them. We'd have an Easter egg hunt, and then we would have competitions, and we would smash the eggs with one another to see whose egg was stronger. And of course, the loser would have the opportunity to peel the shell off and then either eat the egg with a little salt on it, hard boiled, or turn it into some egg salad and make an egg salad sandwich, whatever we would do. We would eat the egg, but we'd try and peel the slabs of the shell off in the biggest pieces possible. Have any of you ever done that? If not, it's great fun. But if you can picture a hard-boiled egg removing the shell, that's kind of what Earth's structure really is like, because we have these lithospheric plates that are giant rock slabs, but these plates are actually moving. Here's another illustration to give to you. I know you know I am a chocoholic. I love chocolate. And, who doesn't love a yummy brownie, right? Well, imagine making an ooey gooey brownie, and you let it set, and the top of that material starts to set first, even though it might be ooey gooey underneath. That's a really good illustration of the lithospheric plates of the Earth, because it's still warm too. And you notice in this picture, we've got some crusty slabs of chocolate solidifying, even though it's still molten or melted underneath. Great picture of Earth's crust. And yum, 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 too. I want to eat that. Yummy. Okay, so what is tectonics? Tectonics is a word that simply means movement of something. In the case of plate tectonics, we're talking about the movement of these lithospheric plates across the surface of the Earth. And there are major plates and there are minor plates, just as if you were to, take the shell off a hard boiled egg, or you remove those chunks off of the surface of a cooling batch of brownies. Some are bigger than others, and likewise with the Earth. The major plates on Earth include the North American plate, the Pacific plate, South American plate, African plate, the Eurasian plate, the Australian plate, the Antarctic plate. These are the major ones, but there are minor ones as well, like the Nazca plate and other plates around the Earth that aren't labeled in this particular diagram. But it's these plates that are moving from one place to another. Now, we don't see it happening necessarily very visibly, and it was first proposed by a gentleman with the name of Alfred Wagner. Hopefully, a familiar name to you because he's our scientist of the week. But Alfred Wagner, and I'll be showing you a video of Alfred Wagner, he wasn't always so popular. He was actually a meteorologist as a scientist, but he liked to examine maps. And he noticed, like if we look at this map here, he noticed that the outlines of some of the continents seem to really fit together. Like South America and Africa, they were like almost puzzle pieces that fit together. And with this observation, he came up with the theory of continental drift, proposed by Alfred Wagner. And this continental drift theory, many years ago, suggested that the Earth's continents are floating from one place to another. Now, we have certainly built upon this theory and actually have proven it, and we can actually observe it today. But for many years, nobody believed it. But Alfred Wagner came up with some different sources of evidence to support his theory of continental drift, which slowly gained momentum and gained support. And so here are some of the forms of evidence that he used. The first form of evidence is from fossils found in the southern hemisphere. And if you look at this map here, you will notice here's Antarctica, here's Africa, South America, Australia. And he noticed, and others noticed as well, that in the southern hemisphere there were certain fossils that seemed to have been found on different continents, even though the present location of these continents are thousands of miles away. The same exact fossils are found in these different locations. But if you were to imagine that these continents, again, like South America and Africa, at some point in the past were next to one another, that might explain why the same exact kinds of fossils are found in present day locations that are thousands of miles apart. One famous example of a fossil is Glossopteris. Glossopteris is a seed fern plant, and as it says here, identical fossils were found in South America, Africa, Antarctica, India, and Australia. And there's no way that these particular seeds could have floated thousands of miles across the current oceans. And the theory is that, well, maybe these kinds of trees were located in the same kind of geographic region many, many years ago in geologic time, when the continents were actually adjacent to one another, and they are currently floating apart from one another today. Hmm, interesting idea, which, by the way, has been proven today. It's no longer really a theory. I mean, it's a fact. Another form of evidence was from rocks. We here in the Northeast, we live in the Appalachian Mountains. And the Appalachian Mountain Range is geologically so very, very similar to mountains in northeastern Africa and northwestern Africa and northwestern Europe, Britain, and Scandinavia. The mountains are so similar to the mountains that we live in here. In fact, it is believed today that those mountains formed at the same time when these land masses were not separated by an ocean, but were actually connected at one point in the past. So, similar rock types with mountains, the shapes of the continents, and the types of deposits formed, similar geologic structures, a great form of evidence to suggest that the continents in the northern hemisphere at one point were much closer together, in fact, connected at one point in the past. Now, to support this evidence from rocks, here's something that can be observed today. Another major form of evidence for the theory of continental drift is the evidence from sea floor spreading. What does this mean? Well, the Atlantic Ocean right now, the Atlantic Ocean looks like this if we were to see a cross section of it. We have North America and South America to the west. We've got Europe and Africa to the east. And the Atlantic Ocean separates them today. And right in the middle of the Atlantic Ocean, we have what's called the Mid Atlantic Ridge. It is a type of mid ocean ridge. And you know what's happening along the Mid Atlantic Ridge right now? It's spreading apart. I'm going to show you a music video that will illustrate how the seafloor is spreading today. I might even teach you a little dance step to go along with the music video. We'll see how much time we have. But the seafloor is spreading. We can measure it. We can so precisely measure that it's moving apart. North America and Europe are moving apart about as fast as your fingernail grows. That's right. Your fingernail, you can measure the growth of your fingernail. Yeah, it takes time, but you have to snip your fingernails every so often, right? And in the course of a year, it might go a couple of centimeters. If you never cut your fingernails throughout the whole year, your fingernail would probably grow about 2 centimeters. That's about how fast the mid ocean ridge is spreading and growing further apart. Given enough time, we have been able to measure how much further the continents are drifting apart from one another. There's a lot of other interesting evidence that we can detect from the mid-ocean ridge, which we'll get into later on. But I just wanted to start you off today with some basic evidence to support the theory of continental drift, which helps to explain the plate tectonics of planet Earth. So, with that being said, we'll use the rest of our time to watch some interesting videos. So, for now, I'll say bye bye.